has always been the most widely accepted position. Observation produces the result. Right? Note, however, that if this is correct, there is something very peculiar about the act of measurement, something that over a half-century of debate has done precious little to illuminate. And hey, but then the rest of the book is, you can't see it from here, but just equations after equations, all mathematics, all calculations. As a matter of fact, quantum mechanics, the way we deal with quantum mechanics in teaching has been characterized by one physicist, David Merman, as shut up and calculate. And hey, I've taught this course many times, and when I teach it, I tell the students, shut up and calculate. You know, if I allude to any kind of mystery, I say, don't worry, it's not on the exam. And you know, when you say that to students, they don't worry about it. Hey, I'll just read the last sentence of the book, how the book closes. I say the book doesn't starts out by telling you observations produce the results, but then it ends, it is entirely possible, last sentence, it is entirely possible that future generations will look back from the vantage point of a more sophisticated theory and wonder, how could we have been so gullible? Okay. Okay, hey, what we're going to do is look at some quantum theory neutral experimental results. Some results that you don't need to know any quantum mechanics to understand. Because the quantum enigma arises directly from what anyone can see in the lab without any consideration of quantum theory's explanation of the empirical facts. But since there are so many physics majors here, I don't want to, I'll say something about quantum mechanics to start with, but then I'll tell you to forget it. What we do is we take a pair of boxes. Am I in the way? We can take a pair of boxes, and I can send an object, photon, electron, atom, it's been done with large molecules, into a semi-transparent mirror. This wave function splits, and here's a hard mirror, total reflection. And the object, whatever it is, can be in the region of the box. And when it's in the region of the boxes, I slam the boxes shut, and the object bounces back and forth in the boxes, in this pair of boxes, you know, forever, well, as long as I want it to. And hey, keep in mind, be open-minded. Hey, be open-minded now. Hey, you're a debate. You're supposed to be open-minded, right? Be open-minded. The object that I'm talking about could be an electron or not molecule, but think of it either as a hard marble, maybe it's like a hard marble, or maybe a wavy fog ball. I'm just going to call it an object. And you know, knowing the object's speed, we close the boxes at the time to trap it, and then the object bounces back and forth in the boxes. But now what I've done is I've crossed out all this quantum mechanical explanation. Forget about it. That's how the boxes were created, but we don't want to talk about that. Because the logic of what I'm going to tell you doesn't depend on that. What we have is we end up with a pair of boxes. You know, a pair of boxes prepared that way, but I don't have to tell you how they're prepared. You have a pair of boxes. Actually, you have you have sets of boxes. You have 4 sets of boxes, and they're prepared identically. Set A, set B, set C, set D. Okay, let's see what we do with them. Presenting the quantum enigma. Hey, you know what I'm telling you is not really hard to understand. People think it's hard to understand because it's so hard to believe what I'm telling you. But it's not that. Okay, hey, here's what I do with each here's box pair set A. I have a whole lot of them here. I take each box pair, and here the wave function of the object. I shouldn't use that word, but your physics majors is in both boxes. I separate the boxes by a distance s. I open a hole in each one about the same time, and I find plink, an object lands on the screen here. Hey, I take that box pair away and slide it out there, and take the next box pair, do the same thing. Plink, 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 plink. I get a lot of objects on the screen. What I find is that there's a pattern. The places they land are separated by this distance d. You know, I do the experiment again by changing the distance, the separation of the boxes, s. Okay, I now find that when I change s, d changes. Hey, in other words, d is a function of s. Hey, each object follows a rule that depends on the spacing of its box pair, each and every object. Something of each and every object must therefore have been in every box of its pair. Hey, the standard explanation for physicists is, of course, interference, but I don't want to go there. All I'm saying is that if I change s, I change this pattern. Hey, therefore, each and every object knew a rule depending on s. Something of each object must have been in both boxes. Hey, because no matter what I do outside here, it doesn't have any effect. Okay, that's the experiment I've done. But maybe it's no problem. Interference explains it, okay? Hey, but with set B, I had 4 sets. With set B, I do a different demonstration. What I do is just open a box and look in. And what I find is each object is wholly in a single box. And no matter how I look in the other box of its pair, that box is totally empty, nothing in it. Okay? Hey, maybe look, set A, box pair set A, had objects that were distributed over both boxes, some of it, whereas box pair set B had objects that were wholly in one box and the other box was empty. Okay? Hey, but look, I had 2 more sets of boxes. And with box pair set C and D, I can freely choose what to demonstrate. I could freely choose to, hey, you may choose to demonstrate that each object was wholly in a single box, or you may choose, at least you think you might choose, you think you're choosing, you think you choose to demonstrate that each object was not wholly in a single box. So the question comes up, what was the physical reality before you choose? Was the object wholly in a single box or was it not? This is the quantum measurement problem. This is the 2-slit experiment done in a rather dramatic way. But realize that it's an enigma. Enigma is a puzzle, a problem, whatever you want to call it, enigma. It's an enigma because, but only because, I believe I could have made the other choice. So that's where free will enters. I just now tell you that I said this experiment could be done with